Thanks. Yeah, I'm very glad we have Uri Feige talking about another very controversial topic. Your first case analysis and approximation, no violence.
So thank you. So this controversial topic was suggested to me by the organizers, and now I needed to fill it up with some content. So there are many things I can speak about, and eventually I chose some subtopic within it. So the plan of the talk is as follows. We'll consider really 5 problems. So max 3 SAT, mean bisection, 3 coloring, unique games, and densest case subgraph. And on each of them, try to look a little at the interplay between algorithms for worst-case instances and for random instances, and to see if one informs the other. So like a question to keep in mind during the talk is the following, that does the study of algorithms that handle random inputs help in designing approximation algorithms for worst-case instances? And in general, the picture can go either way. So sometimes they're related, sometimes they're not related. Let's say something that often happens when we design algorithms for worst-case instances is they really prepare themselves for the worst, and when a very easy instance comes, they screw up completely and like give the worst possible approximation ratio on very easy instances. But I'll try more to say that studying random instances helps in the design of algorithms for worst-case instances. So let's start with max 3 SAT. So here we have a 3CNF formula with n variables and m clauses. And the goal is to find an assignment that maximizes the number of clauses that are satisfied. So this is a well-known problem. It's well known that a random assignment satisfies 7/8 of the clauses in expectation. So each clause by itself has probability 7/8 of being satisfied. And by linearity of expectation, that's what you get. And this already gives an approximation ratio of 7/8, because at most you can satisfy all the clauses. And Hastad proved that achieving an approximation ratio better than 7/8 is NP-hard. So this is what's known about worst-case instances. So if we look at random max SAT, let's go over it slowly to understand what we mean by, let's say, approximation algorithm for random instances. So here we have to specify a distribution over random instances, and the distribution is you just pick the formula completely at random. Each literal in every clause is chosen independently at random, like what the variable is and what its polarity is. And now what do we mean when we say we have an approximation algorithm with ratio rho for random instances? There is this issue of random. It doesn't always have to work. So what do we mean by this? So if the algorithm chooses to output an assignment, the assignment better be of the following form, that the number of clauses that are satisfied by the assignment is guaranteed to be at least, let's say, this rho fraction times the number of clauses that can be satisfied by the optimal assignment. So if it outputs an assignment, from it there's a guarantee both of how many clauses the assignment satisfies and what's the maximum possible number of clauses that can be satisfied. And the ratio between these two numbers is rho. But it's allowed also not to output an assignment. It can just say don't know, but it cannot always say don't know. So with probability at most half over the distribution, over random instances chosen from the distribution. So that's the notion of an approximation that we shall consider for random instances. And here, so no algorithm is known or even conjectured to achieve an approximation ratio better than 7/8 on random instances. Let's say when the number of clauses is some very large constant times the number of variables.
So here the difference between Las Vegas and Monte Carlo is not that important, right?
So in a sense, it's more like Las Vegas or something. I don't know if Las Vegas.
You can always check.
So it's not like BPP in the sense that there's an error. There's never an error in what you return. You always answer correctly. You just or within the approximation ratio that you need to achieve, but you're allowed not to answer. So like, there's no notion of errors here. It's just the probability of not answering. Okay, so we see that at least for 3SAT, random instances appear to be as difficult as worst-case instances, because for worst case, we cannot do better than 7/8, and for random, we cannot do better than 7/8. So we can ask ourselves, can we prove NP hardness for random instances? Can we prove that we cannot do better than 7/8 on random instances? Unfortunately, I'm not aware of any technique of proving NP hardness results for random instances. As far as I know, there are no such results. So we can try to ask whether the pattern that we see here is more general. So suppose that the problem is NP hard to approximate within a ratio better than rho in the worst case. Then we can ask ourselves, is there some natural distribution? So by natural, I mean something that, let's say, you can sample from over inputs, for which it's hard to achieve an approximation ratio better than rho. And here I don't mean, when I say hard, I don't mean NP hard, because we don't know how to prove NP hardness for random instances, but at least that all our algorithms fail. So is this for 3SAT, this is what happens? Does this happen for other problems as well? Okay, so any questions about max 3SAT? Yes?
Are there any kind of natural random problems where we know NP hardness?
As far as I know, no. There are other notions of hardness, sometimes that you can invent around random instances. Let's say conjecture that some problem is hard and then this other problem is also hard. But they haven't been tied, let's say, to hardness of 3SAT, let's say. Okay, so now let's look at a different problem, mean bisection. So the input is an n-vertex graph, and we want to partition its vertex set into two equal size parts, minimizing the number of edges in the cut. So here this would be a bisection. There are 3 vertices on each side, and there are 2 edges in the cut. So what do we know about mean bisection in the worst case? So if we look at approximation algorithms, so here what you're allowed to do, you still need to output a cut which is completely balanced, n over 2 vertices on each side. And you ask by how much your bisection is larger than the minimum bisection. So there's an approximation algorithm with an approximation ratio of order of log n. I'll say a little bit more about this algorithm later. And the only hardness results known is that assuming that NP does not have sub-exponential time algorithms, there is some constant, maybe close to 1, such that you cannot have an approximation better than that constant. So there's a large gap in what we know here. People also considered bi-criteria approximation. So these algorithms are allowed, instead of outputting a completely balanced cut, they're allowed to output an almost balanced cut, let's say 49% of the vertices on one side, 51 on the other side. And for such algorithms, the approximation in the number of edges in the cut improves to order of square root of log n. And also here, there's some hardness of approximation, assuming that NP does not have sub-exponential time algorithms. So now let's look at random instances of bisection. So here, let's start with the simplest random instance, like we did with 3SAT. Just take a random graph with m edges and suppose that m is much larger than n, just completely at random. So in this case, the minimum bisection, it's not hard to see by Chernoff bound and union bound, that the minimum bisection is slightly, very close to m over 2. There's no good bisection in such random graphs. Any bisection would cut roughly half the edges. Also, the maximum bisection would be of roughly the same value, slightly above m over 2. And indeed, we have algorithms that certify this in polynomial time. That is proof for your particular instance that there's no good bisection. These are spectral algorithms. So let me explain a little. So random graphs, if the number of edges is large enough, they are nearly regular. So let's say that the average degree is d. So they are nearly d regular. Almost every vertex has degree close between, let's say, d plus minus square root of d. So if we look at the adjacency matrix of such a graph, it's not hard to see that the largest eigenvalue of the adjacency matrix is roughly d. Now, because random graphs are very good expanders, the second largest eigenvalue of the adjacency matrix is order of square root d with high probability. And you can, in fact, certify it. You can compute these eigenvalues and see that this is indeed the case. But on the other hand, if there would have been a small bisection in the graph, it's again not too hard to see, I will not prove it, that in that case there should have been not just one large eigenvalue of value linear in D, but at least two. So the fact that you don't find a second one is evidence that the graph does not have a small bisection. So on random instances, if they are dense enough, the approximation ratio for mean bisection is close to 1. So if we recall what happened in the worst case instances, we did not have good hardness results, and also for random instances, they don't seem to be hard. Yeah.
So for smaller than m over 2, did you mean like m over 3 or m?
Yes, m over 3, let's say. And I'll also get to this here. No, I wanted to be 1. Sorry, let's go back. Okay, other distributions of random graphs. So you might not like the fact that, that in this model of random graphs, there really is no small bisection. So you can ask what happens on random graphs which do have small bisections. So how would you choose such a graph? So one way of trying to do it is sample uniformly at random from all graphs that do have small bisection. That would be one model. So it turns out that this model is pretty close if the number of edges is large and the bisection is fairly small, to a model of a planted bisection. So statistically close. And the model of a planted bisection is you first decide on your bisection, then sample edges between the two parts with some small probability, and within each of the two parts with high probability. So this would make this bisection the smallest bisection. And it turns out that for all sufficiently dense graph with minimum bisection, if it's significantly smaller than m over 2, and here you don't need something like m over 3, some m over 2 plus minus some low order terms would in fact be enough. You can find a minimum bisection in polynomial time, and moreover provide a proof that this is indeed the minimum bisection. So you actually find the exact minimum, not an approximation. This was done already in '87 by Gopana. It uses semi-definite programming. So one way I think of semi-definite programming is that it's like a technique that combines two aspects. One, the spectral techniques that we've already seen, and another, some linear programming component. And it's open whether there's some, or I don't know, at least, is there some distribution over graphs for which it seems plausible that achieving a constant factor approximation is hard. So this I don't know for minimum bisection. So let's look a bit about the algorithms involved. So for worst case instances, the current best bicriteria approximation algorithm uses semi-definite programming, which is also good for random instances. And in fact, it adds constraints, the triangle inequalities, that are not used for the random instances. If we look at true approximation algorithms that are not bicriteria, they have to output an exact bisection. The previous best algorithm used the bicriteria approximation algorithm as a black box and lost an additional log n factor. But the current best approximation algorithm by Rake, so it does not use semi-definite programming at all. It's based on a different concept. It's randomized embeddings of graphs into trees, where every edge suffers an average load of order log n. So let me spend just one slide explaining what this concept is. So think, let's say, this is your whole graph, both the black edges and the blue edges. And think of, for simplicity, you pick a spanning tree in this graph. So the load of an edge in the spanning tree would be the number of edges that need to use it as a path, as part of a path between the endpoints now that the edge was removed. So let's say if I look at this particular edge, so its load is 1 for itself, but also because now I just have the spanning tree, this edge no longer exists, so instead it has to be routed through this path, the unique path between its endpoint, so it also contributes to the load of this edge. So the load of this edge is 2. The load of this edge is 3, because also this edge needs to be routed through it. So that's the load of an edge. So if we look at this particular tree and look now at the cut in the tree, so the cut contains 2 spanning tree edges, so 2 of the black edges. It contains 3 graph edges, so also this edge. And who really accounts for this edge? It's this edge, because the load of this edge would be 2 because of the existence of this edge. And it also contains another, if we look at the load of the cut, it really is 4 because the load of this edge is 2. So even though this cut cuts 3 edges in the graph, its load when is really 4. So what Rake did was the following. He showed that every graph can be embedded, for simplicity, let me say distribution over spanning trees. So I'm cheating a little bit here. So every graph can be embedded into a distribution over spanning trees, such that for every edge in a graph, if I look at its average load over all spanning trees, it's at most log n. And okay, so that's what he showed. And
so
once
many of them, the load is 0.
For some, so in some place, so your load might be, let's say for this edge, let's say now the load is 0. Yeah, it's not part of the spanning tree. Yeah. So, but over the whole distribution, your expected load is not more than order of log n. And then the point is that once you have trees, on trees, all kind of cut problems like bisection become easy. You can solve them exactly in polynomial time using dynamic programming. So now on each of these trees, you can solve the minimum bisection using dynamic programming. And you take the smallest one that you find, and it's not hard to see that this is an order log n approximation to the original problem. So this is a different kind of algorithm for cut problems, and maybe a question to ask here. We have all these, if we look at random instances, we somehow do not seem to use these kind of algorithms for random instances, so do they help? And another question, often when we prove that certain algorithmic techniques do not work, like the SOS hierarchy does not do something, I'm not sure that these types of algorithms are captured by SOS hierarchies. So if people are interested in proving that certain algorithms do not work, so here's a class of algorithms for which I don't think there was much work in trying to show where they fail. And part of the problem is that you have a distribution over trees. It's enough that one tree would be very good and you're done, even if all the rest of the trees in the distribution are bad. So this is what I had to say about mean bisection. Any questions on this? So now let's move to a different problem, tree coloring. So this is a tree coloring of this graph. So you color the vertices by 3 colors such that no edge is monochromatic. Every edge sees at least 2 colors, exactly 2 colors. So what do we know about the problem of mean three-coloring? So the problem is the following. You're given a three-colorable graph, and you want to legally color it with as few colors as possible. So every edge has to be legally colored, and you want to use as few colors as possible. So this problem is NP-hard. And in fact, it's NP-hard even if you have a three-colorable graph. To color it with 4 colors is also NP-hard. It's open whether it can be colored with 5 colors, whether there's a polynomial time algorithm that does it with 5 colors. There's some evidence that it's hard, let's say if you believe in unique games or things like that, but no NP-hardness result. So here I'll be interested in graphs of maximum degree D or really average degree D. It would be the same. And D, you should think of it as it can also be a function of n. So D can be some n to the delta here. So for these graphs, greedy coloring, if we look at maximum degree D, greedy coloring uses at most D+1 colors. Whenever you reach a vertex, whatever colors its neighbors are using, you still have 1 color available for the vertex. And the breakthrough result of Karger, Motwani, and Sudan used semi-definite programming to show that in fact you can, if the graph is 3-colorable and degree maximum degree D, in fact you can color it with roughly D to the 1/3 colors, the cube root of D colors. So this uses a notion of vector 3 coloring that I'll briefly explain. So the picture to have in mind is this picture, that if a graph is 3-colorable, you may think of trying to embed it in the plane in the following way. You partition it into color classes, so 3 color classes, and put 1 color class on this vertex, 1 on this vertex, and 1 on this vertex. Each one of them is a unit vector if this is the origin. And the angle between any 2 of them is 120 degrees, so the inner product between these 2 vectors is -½ So really what happens, within each color class, you don't have any edges. So all edges go between different color classes. So if you have an edge, the inner product between the corresponding vectors, if you have an edge, is -½ or let's allow it to be even the angle to be larger, so even more negative than -½ Whereas if you don't have an edge, so the pair of vertices are either in the same color class or in different color classes, so the inner product is -½ or more positive. So I'm allowing some slackness here. So really, you could demand a bit more, but I'm not requiring it. So every 3-colorable graph is vector 3-colorable by what I've shown here. And it turns out that SDP finds a vector 3 coloring in polynomial time. So a vector 3 coloring is something that satisfies these equations. It's not a 3 coloring because it doesn't have to lie in the plane. It might lie in higher dimensions. These vectors might be in higher dimensions. And what Karger, Motwani, and Sudan showed that if you have a vector 3 coloring, then you can round it to get a coloring that uses D to the 1/3 colors. So you can ask whether you can round it to use fewer colors. And there are examples showing that this is not the case. So these examples are anti-geometric graphs. So they are constructed as follows. You place n vertices on a sphere of, I'll say, the dimension of the sphere, I'll call it dim. Think of this dimension as roughly log n. Edges connect, or even smaller. Edges connect vertices that are far apart. So if you look at the center of the sphere, they make an angle of at least 120 degrees, similar to what we had here, that the angle had to be large if there was an edge. So the same thing happens here. If the angle is large, you put an edge. So these graphs, by definition, are vector 3 colorable because with each vertex we already have associated a unit vector, and if there's an edge, the angle is large. And the chromatic number, the number of colors you need in order to really color them, legally color them, is indeed d to the 1/3, if you set the dimension correctly. So this shows that the rounding of Karger, Motwani, and Sudan is optimal. So often approximation algorithms for 3 coloring are expressed not as a function of the degree, as I did here, but as a function of the number of vertices. And here, let me just go over a sequence of results. So the first approximation algorithm by Wigderson was n to the 0.5, square root n, meaning that if you have a 3-colorable graph, his algorithm could color it with square root n colors. Afterwards, there was a sequence of papers by Blum. Whenever I give, usually when I give 2 dates for a paper, one is the conference version, the other journal version. Okay, just so that you see the timeline. So Blum, in a sequence of papers, improved it to 0.375. Then Karger, Motwani, and Sudan, in the algorithm that I showed, they achieved d to the 1/3, which translates, if you pair it together with Wigderson's technique, to n to the 1/4. Then Blum and Karger paired the semi-definite programming with the techniques of Blum to get this improved result. And then the semi-definite programming was strengthened with triangle constraints to get a small improvement. And then people looked at hierarchies as well and got an even additional improvement. And as far as I know, the current bound is slightly below 0.2 with rather complicated work leading up to it. But the d to the 1/3 was not improved. So from my point of view, I find it more interesting to try to break the d to the 1/3 than to keep on improving the dependence on n. Okay. Because it somehow appears that things are getting more and more complicated, and I would like them to get simpler in a sense. So the question is, how can we attack this problem of improving the...
So d to the 1/3 for random instances, because the lower bound is...
Okay, so let's go now to random instances. So before that, let me talk about what I described before. I called it mean 3 coloring. Let's talk for one slide on max 3 coloring before going to random instances. So what's max 3 coloring? So again, you're given a 3-colorable graph on n vertices. And now the number of colors that you're allowed to use is only 3. And you want to color as many vertices as possible without violating any edge. And some vertices are allowed to remain uncolored. So you want to find, let's say, the largest induced subgraph that you can legally 3-color. So this is a different notion of approximation for 3 coloring. So this is very strongly related to mean 3 coloring, because if you have a mean 3 coloring that uses k colors, then you take the 3 largest color classes and you have a 3/k approximation to max 3 coloring. And the connection also goes in the other direction. If you have a row approximation algorithm for max 3 coloring, you can use it iteratively to get an algorithm for mean 3 coloring. Because you color a row fraction of the vertices, remove them, now use 3 fresh colors, again color a row fraction of what remains, and so on. So you suffer an extra loss of a factor of log n in the approximation, and in some cases, depending on the form of this row, you don't even lose this extra log n. So all known, I think all known, mean 3 coloring algorithms, or all the good ones, are derived from max 3 coloring algorithms. What the rounding techniques for the semi-definite programs do is, let's say, essentially find one independent set, but you can think of it as finding 3 independent sets, so that's a max 3 coloring, and then recursing. So a remark that I wanted to make is when we look at random instances, this correspondence might break down. So it could be that you have a good max 3 coloring algorithm, that you manage to color almost all the graph, let's say, with 3 colors, it does not necessarily imply that you'd be able to color all the graph with a few colors, because the subgraph that remains might not be from the same distribution from which your original graph was, and so the guarantees might break down. So this is just a point to keep in mind, that for random instances, there is this distinction between these two problems. So let's start with a few results about random instances. So there is the random planted model, which was introduced by Kutsera in 1977. So you think of the graph as being generated. Okay, there are several ways of presenting how it is generated. I'll present one way, which I refer to it as the hosted framework. So you start with a host graph H, sampled at random from GNP. Each edge is present with probability P, so this is not three-colorable. And then in it, you plant a random three-coloring, which means you partition the vertex set into 3 sets. And within each set, you remove all the edges. So the graph becomes three-colorable. And okay, the expected degree before planting, let's denote it by D. Okay. So just as an example of the model, so you have a random host graph. So this is not very random, but who knows? Okay. And a poor random generator. Okay. You planted it in it three-coloring. Now you see there are certain monochromatic edges, so this is illegal. So you remove them from the graph. You remove the colors, so that, and this is the graph that you see as input. And now you need to three-color it. So the algorithmic task, you get this graph as an input. You never see the original graph H that you started with, or of course not the planted coloring. And you need to find a legal three-coloring, not necessarily the planted one. So any legal three-coloring is fine. So it turns out that at sufficiently high densities, again, there's a phenomena that I described also in bisection, a random three-colorable graph is distributed like a random graph with a planted random three-coloring. So if you want to sample a random three-colorable, dense random three-colorable graph, this procedure gives you a sample from essentially the right distribution. And also it turns out that these graphs can be colored using spectral algorithms. This was done by Alon and Kahala, and also semi-definite programs, which are stronger, would also three-color such graphs if the degree is large enough. And in fact, the algorithms can be made to work even at much lower degrees when the distribution of the planted model is already different from the distribution of random three-colorable graphs. The algorithms still continue to work, so they work pretty well. So in any case, it seems that random instances do not capture the difficulties of worst-case instances in the case of three-coloring. So what can we do now? We can try to look at the other distribution of random instances that maybe better capture the difficulties. So a natural place to look is this geometric or anti-geometric graphs that we looked before that gave the integrality gap for the semi-definite program for vector coloring. So the host graph, if we look at the framework that we had before, is a high-dimensional anti-geometric graph. As I described before, you scatter n vertices at random on a d-dimensional sphere. And you place edges between vertices that are far apart. And then in this, you plant a random three-coloring. So you partition the set of vertices at random into 3 parts, not respecting the geometry of this picture. So every vertex independently receives one of the 3 colors, and edges which are monochromatic are removed. So this is the new distribution of random instances. You can ask yourself now, is it difficult to find a three-coloring in this distribution, or how well can you approximate three-coloring here? So the challenge is as follows. The input graph is generated as I described here. As input, you don't get the geometric representation, because if you got it, then you'd know by the fact that an edge between two distant vertices is missing, you know that they're probably that they have to be of the same color. So you get it as an adjacency matrix without the geometry. And or a different version of the same question is already in the model. You don't place between every pair of vertices which are far apart, you place an edge, but only between some of them. That's so in this case, just by if you had this geometric embedding, it would not tell you which vertices need to have the same color. So what do we know about it? So we know that when the dimension is small, up to something like close to 5 log n of this sphere, we can find in polynomial time, in fact, the planted 3 coloring. And this number is not just an arbitrary number. It has some geometric significance that I will not describe. So at this point, the degree of the graph is roughly n to the 0.3. And beyond that, we are not sure what happens. So an open question is to design an algorithm that colors these graphs in all dimensions, regardless of the dimension of the sphere. Yeah.
So for these graphs, the STP is unlikely to work because you already
Okay.
proved.
So this is exactly the difficulty here. The SDP, even without the planting, thinks that the graph has a 3 coloring. So like it's not going to point you towards the coloring. It might help you find the embedding. And this might help you find the coloring. But also to prove that it helps you find the embedding, that's not so obvious. I don't know. I mean, the embedding that you started with, it might give you a different embedding. So there are certain candidates. It's not that we don't have ideas what to do in this setting. It's just that we don't know how to analyze what happens. And let me describe one idea that we were trying to follow. So this is the vector 3 coloring semi-definite program comes in different versions. So I consider this version where when you had an edge, the angle had to be 120 degrees or larger. Now in this picture, when you have an edge, the angle is exactly 120 degrees. So you can write a stronger vector 3 coloring relaxation saying that if you have an edge, the angle is exactly 120 degrees. And now the question is whether these anti-geometric graphs, so whether these graphs, so these graphs have an embedding the way they were defined, where when you have an edge, the angle is at least 120 degrees, but it might be larger. Do they also have an embedding in which when there's an edge, the angle is exactly 120 degrees? If not, then the SDP would recognize, let's say that before the planting they are not 3 colorable, so after the planting, probably the solution that it gives is correlated with the 3 coloring. So that's the hope here. And this might be a way to improve over the d to the 1/3 approximation ratio because it handles the most difficult class of instances for the previous bound. So I think so this is a nice geometric question. You can treat it like ask it even independently of its application in coloring, whether when you have an embedding of points on the sphere, you can embed them in a different sphere, maybe in higher dimension, satisfying some other properties. At best, this approach would lead to some approximation ratio, which would still be d to some power, smaller than 1/3, maybe 1/10. I don't know what the explicit constant would be here. I didn't compute it. You can compute an explicit constant. And this follows from work of Moses. So that even the strong SDP has an integrality gap, but not d to the 1/3, something smaller. Okay, so any questions about coloring?
So what is the algorithm of that leads to you mentioned that there is a polynomial time algorithm.
For certain.
What is the idea?
So like it's a sequence of algorithms. You start like with the, like some of the algorithms that work for random graphs, for random instances prior to the semi-definite and spectral techniques, like counting common neighbors and things like that. They work at when the sphere is of very low dimension. As you increase the dimension, it becomes more complicated, but they're combinatorial. They don't, at least the algorithms that we had. Yeah.
So, big question. So you're sitting in log n dimensions, right?
Yes.
If I pick a random subset of big constant times log n,
Yes.
maybe coloring them is enough to give you.
Yes, so this is a partial answer to Chandra's question.
Okay.
Some of the algorithms look like you take a sample, try to color it, and extend the coloring, and so on. So yeah, these are the kind of algorithms that work. But as the dimension gets larger, the graph becomes, in a sense, more sparse. The degree goes down, and they stop working. So.
And on those lines, if the three coloring is sort of strongly unique or something, then coloring a sample might tell you the whole story. Is that?
That's true in low dimensions. So in low dimensions, you can prove two things. You can prove that the coloring is unique. In higher dimensions, we don't know. And the other, you can prove, if the dimension is low enough, that if you color a small sample, you can extend it to the coloring of the whole graph. But for this, the dimension has to be small. Okay, so now I'll move to a different problem, unique games. So I'll describe it as a coloring problem. So we have a graph, we have k colors. On every edge of the graph, you have some permutation that is specific for that particular edge and given as part of the input. And the goal is to color the vertices of the graph using these k colors. And you want to maximize the number of legally colored edges. Where an edge is legally colored, if the color of one endpoint, when you apply the permutation of the edge to it, you get the color of the other endpoint. So that's unique games. And I suppose most people in the audience heard of the unique games conjectures that says that for every epsilon, think of epsilon and delta as being small, close to 0. You can choose sufficiently large k such that it is NP hard to distinguish between instances in which you can legally color almost all the edges and instances in which any coloring legally colors only a very small fraction of the edges. That it's NP hard to distinguish between these instances. So let's say a few words about random instances. So first, maybe I should say there's extensive research on the unique games conjecture and its implications, and I don't have time to mention it even. There's so much. So random instances of unique games are approximable much better than what the unique games conjectures say. And in fact, we have much stronger statements. So these are taken from these two works. So the beginning maybe was this work of Aurora et al. That you can think of it as unique games on, when you say expanding constraint graphs, as a special case, random graphs. And this really drove this point home by looking at several models. So let me describe these results. So here are 4 semi-random models for unique games. So not just random, they're semi-random in the sense that there's also an adversary that chooses some parts of the graph, of the input instance. So we can think of an instance as generated in 4 steps. So if we want to generate an instance, a yes instance of the unique game, in which almost all edges are colored legally, we can generate it as follows. We first pick the graph, the constraint graph. Then we pick the permutations along the edges, and we pick them in such a way that the instance is completely satisfiable. So the way of doing it, you can think of a coloring of the graph and then pick permutations that are consistent with this coloring. Thereafter, you pick at random a small set of edges that you want to corrupt, and then, or not at random, arbitrarily, and then on these edges that you want to corrupt, you choose some other permutations that would not fit, so that these edges would not be satisfied. So that's a general recipe of choosing how either you can choose or an adversary can choose an instance which is 1 minus epsilon satisfiable. And the theorem says, it sounds very strong, like, so if epsilon is small, think of it very close to 0, and at least one of the above 4 selections was made at random. You have here 4 choices, so you can allow an adversary to choose any 3 of them, do whatever he wants in any 3, but one of them has to be random. Then there's a randomized polynomial time coloring algorithm for which most edges are legally colored. So that's an approximation ratio much better than what the unique games conjecture says that it's hard to do. So in fact, it's not just really one algorithm. It's you need to somehow tailor the algorithm to which step is random. But in general, you can think of it as one algorithm.
Does the algorithm know which of the...
You can try all 4 algorithms, and one of them would work. Okay, so as many results on random instances, also here there's some condition on the average degree of the graph. Like the graph has to be of large enough degree for the algorithm to work. So it looks like unique games, at least if we look at evidence from random instances, doesn't seem to be a difficult problem. So any questions about, yeah?
I thought you would say by semi-random I can delete some of the edges from the random graph. Sort of
So
like you do in your models.
There are many different semi-random models, so that's one of them. We might hear maybe in that.
Does the deletion make it harder here, or is it still easy? Do you know? I take the random graph, but I'm going to delete some edges.
Yes. So it still remains a random graph. So what if you delete them at random? Okay. I mean, you can start playing with the model more and try to see how far you go. But just, let's say, deleting edges, you can probably incorporate it. It's just a new graph. So I'm not sure if it would be 4 out of 5 in this case. But my first intuition would be that it would not change the picture by much.
Well, I can skew the degree distribution, all kinds of things I can do, right? So anyway.
Yeah, but even as we said, in some of these models, the graph is not random, and you can still do it. So you don't need the graph to be random. It's enough that some other aspect is random for these algorithms. So that's the point, is that even if the graph is not random, you can do it. Okay, so the last problem I want to look at is dense K subgraph. So here the input is a graph on n vertices and a parameter K. And the goal is to find a subgraph induced on K vertices of highest average degree that induces the largest number of edges. So this problem is NP-hard. It generalizes K-clique as a special case. The best approximation ratios known are of the form n to some power delta, roughly 1/4. And as far as we know, maybe you can approximate it within a ratio of 2 in quasi-polynomial time. In polynomial time, if you could do it in polynomial time, then NP would have sub-exponential time algorithms, but maybe in quasi-polynomial time you can do it. So it's again wide open, this problem. So here's a random model for the dense K subgraph problem. So you have some host graph G, a large graph, and this is a random graph with edge probability P. And in it, you take a set of vertices and plant, instead of the original graph, a graph H of higher edge density Q. So if this Q is sufficiently larger than P, this is going to be the densest subgraph in your graph. So this is a random model. So the question is, can you, let's say, detect H in such a random model? And here, okay, that's a reminder of the model. So here's something that you can do. So think, for example, that the average degree in H is larger than the number of vertices in H to the power of 1/3, whereas the average degree in G is smaller than n to the 1/3. Okay? what would happen in that case. So it's not hard to see by, let's say, a union bound that G would not have any clicks of size 4. We just do the expected number of clicks of size 4 is going to be smaller than 1. And it's known also that H, graphs whose average degree is more than the number of vertices to the 1/3, will have clicks of size 4. So there's something.
The first 1/3 has to be strictly greater than the second 1/3, no?
Yeah, I mean.
By a constant.
So here let's think 1/3 plus epsilon, and here maybe 1/3 minus epsilon. Think of it this way. Okay, so in this case, we will detect the fact that we planted H inside G. And this is a starting point of an algorithm. So in general, we can detect the existence of H, that H was planted in G, whenever the log density, like the power, when we look at the average degree in H. So that's the average degree, and we take log to the base of k. If this is larger than log to the base of n of the average degree in G. Because whenever it's larger, there is a certain small induced subgraph that would appear in H, but will not appear in G, by the same kind of argument, by union bound. So we can look for these subgraphs, and if they exist, we know that some H was planted. So, for example, for K4, the log density, the critical log density is 1/3. For log density above 1/3, K4 appears. Below 1/3, it doesn't appear. So this was used as a starting point, or the key insight that led to improve the current best approximation ratio for dense case subgraph in the worst case instances, n to the 1/4. So this log density approach, that you get it from these random instances, let's say inspired, and was the basis for the currently best approximation algorithm for dense case subgraph. And here's an open question around this. So suppose that G, now the large graph, its average degree is slightly below square root of n. You plant in it a subgraph of size square root of n, and its average degree is slightly below, but more so, than n to the 1/4. So the log density of this is slightly smaller than the log density of this graph. Now, if you look at this particular instance, if you look for dense case subgraph, or you're looking for a subgraph of size square root k, so H has average degree roughly n to the 1/4, slightly below. Sorry, that's k cube. No, I should have been k to the k to the 0.48, which is more like n to the 1/4. That's a typo here. So the degree here is like n to the 1/4, not k to the 1/4. So H has degree roughly n to the 1/4, whereas G, if you just take a subgraph within G of size square root n, it would be rough at best you'd be able to pick something like a 3 or something. The average degree would be constant, maybe logarithmic, not more. So this is an instance where, to get an approximation ratio better than n to the 1/4, or close to n to the 1/4, you better detect H. And the open question is, can you detect the existence of H? And here I arrange it in such a way that the log density of H is smaller than the log density of G. So in terms of small subgraphs, H does not have small subgraphs that G does not have. Okay? So the question is, can you detect H? And this currently is the obstacle to improving over the n to the 1/4 approximation ratio for dense case subgraph. And let me make a bold conjecture, okay? That if you improve just this random instance, you'd be also able to improve the worst case instance. That this random instance really captures the difficulties in the worst case. And the reason I'm making this conjecture is this is what happened in the previous algorithm. Like, once we were able to deal with these planted instances, everything with extra work worked also for worst case instances. Okay, so let me summarize. So we've seen 5 problems. So for max 3 SAT, random instances appear to be as hard as worst case instances. For mean bisection, random instances are easy. For mean tricoloring, also random instances are easy, but there is an interesting distribution that is worth studying, that of these random anti-geometric graphs. And it could be that by studying it, you'd also be able to learn something about worst case instances. For unique games, semi-random, or maybe I should call them quarter-random instances, because the adversary fixes 3 parts and the random aspect is just 1 part. So even these instances are easy, so it's not clear what the difficult instances should look like. And for dense case subgraph, I would say this is like a success story in the sense that this is a case where really by looking at random instances, we got improvement in worst case instances. So this is like a template I would like to follow also for other problems. So I'll end here.
For the dense case subgraph, so the detection algorithm, is it sort of clear how you can turn it into like actually finding the subgraph?
Not clear. I mean, the paper is not easy. I mean, there are many steps to do beyond this. Yeah. So I didn't think of them so much, so I don't have anything to say. Yeah.
Otherwise, let's thank the speaker again, and we have a half an hour.